Okay, the next conversation, I'm just going to keep going with the rapid fire videos. This is now leading more into the actual work we're going to be doing this week. We're going to be looking at a series connected circuit. But before we get right into that, let's just talk a little bit more about how we calculate. Actually, wait a minute, before I go there, let's talk about this. We recognize that as a complete circuit when we're talking about AC. In a DC circuit, we would never draw it that way, right? You need the complete loop in order for current to flow. The part that's not drawn here, that's understood, is that this is line 1, okay, and over here we have the neutral. What makes this the neutral, or one of the features of a neutral, is the fact that it's grounded. So if we accept the fact that this arrow means that this end of that circuit is connected to ground, there's the connection that makes that a complete circuit. Okay, so those are the extra details that are not included, they're just understood. Okay, when we're drawing an AC circuit, we typically just draw it like that. Okay, but it is most definitely still recognized as a complete circuit. It must be, or there's no current flow. Right? Good. Okay, so that's the image. Now, back to the conversation about connecting inductors in series. So the question is, what is the total induction in this circuit? Or what is the total inductive reactance in this circuit? Okay, so let's talk about that in terms of the reactance. Okay, because that's the way we can build from our current understanding. Okay, so my question is, if those were resistors rather than inductors, how would we calculate the total resistance in our circuit? Okay, so it would be RT equals R1 plus R2. Right? When you connect resistors in series, how do you calculate the total resistance? Just add them up. Okay, so these are resistive-like values. We call it reactance, okay, but we can think about it, conceptualize it in the very same fashion, okay, so that we can say that XLT, the total inductive reactance, equals XL1 plus XL2, okay, so we can follow the rule that we already know, okay, in a series circuit. Just add up the resistances. The same is true in a series circuit, just add up the reactances. Okay, so we can do that, add them up. Okay, so now we come back and we ask the question, well, how do we figure out the total inductance in the circuit? Well, our circuit, or our equation rather, let me throw it here in the middle, says that L equals 2 pi F, that's XL is equal to 2 pi FL, okay? And L and XL are directly related to each other. As L gets bigger, XL gets bigger. Or as XL gets bigger, L gets bigger. They are directly related. They behave in the same fashion. So if the reactance gets bigger just by adding up all of the reactances, the total reactance is simply the addition of all of the reactances. Okay, mathematically we must be able to say the same thing with the inductance. Okay, because inductance and reactance are directly proportional, right? Directly and linearly proportional. They're both going to go up and down in the same fashion. So the total XL is bigger just by adding all these up. Same will be said for L. So LT equals L1 plus L2. Okay, so I could tell you that L1 equals 0.5 henries and L2 equals 250 millihenries, and you can add them up, and the total inductance is 0.75 henries. Sorry, that's supposed to be an H. That's better. Okay. See what I did there? I went from henries to millihenries. Everybody's good with their metric system conversions. I'm going to be doing that kind of stuff, just throwing it out there randomly to keep you on your toes. Okay? Just add them up, whether we're talking about the inductive reactance or whether we're talking about the induction itself.